So we didn't quite finish this last question, so let's see if we can finish off a couple of the questions. Find the times when the velocity is 0. Well, if I recall correctly, this is the equation for velocity. So my velocity is going to be at 0 there, 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 and there. And look at what's going on with the original graph at those points. Those points, it's either at its highest point or it's at its lowest point. So each of those values is where the position is stopped going up and is starting to go down. So for that split second, when the spring is at its highest point or at its lowest point, where it stops going up or going down. So those are the points we're going to call them. Looks like 0, 3 pi over 2. Looks like at 3 pi. Looks like 9 pi over 2. And at 6 pi. Those are all the places where it's at its maximum or minimum. Whereas at its maximum value is the velocity at its maximum, we're going to pick this 9 pi over 4 value right here. And it looks like 21 pi over 4. And we want to know where the mass is at that time. And those are mass values of 0 at those times. And what is the minimum? The minimum looks like this value here. Looks like at that value there and that value there, not this value. I'm looking at the wrong graph. So the velocity is at a minimum at 3 pi over 4 and 15 pi over 4. And those values are where your mass values are equal to 0 also. Very cool. Now let's take a look at some 7.5 graphs of tangent lines with the reciprocal functions. So if we're going to graph the tangent function, and my tangent function we know has a period of pi, and the domain of each goes from, since the period is pi, and half of it is to the left of it, and half of it is to the right of it, here is what the tangent graph looks like. So the domain of one is from negative pi over 2 to pi over 2, but since it's a period of pi, we're going to say we can add pi n to each of those asymptotes, and we would get another set of asymptotes. Our range looks like from negative infinity to positive infinity for tangent. Our period, we said, was pi for tangent and cotangent. And our asymptotes happen at pi over 2 plus pi n. And if my n is negative 1, I get this one. And if my n is positive 1, I get another one over here someplace at 3 pi over 2. Our x-intercepts happen at 0, the center of this party, and then it's going to happen every pi in either direction from there. Now, we know that there's a whole group of these things, so if I say, oh look, over here there's some more, and over here there's going to be this part here, we're going to go through pi, and it's going to continue to go up. So we know that there are more than one of these tangent things. There's every pi, there's a new one. Oh, look at that. There's my graph. And all that pretty information that I gave. All right. So then, let's talk about the reciprocal of this tangent. So if my tangent graph is here, we know that the reciprocal of that is the cotangent. So if I put in the cotangent, because the tangent is already graphed, the cotangent goes down from left to right, and it would be look like that. And the period remains the same, and the graph, okay. So, yeah, that's not the cotangent. That's the reciprocal. That's the inverse of that. Let's go the other way. The cotangent is different. So the cotangent, because 0, the reciprocal of 0 is undefined, my cotangent graph would have an asymptote at 0, and it would also have an asymptote at pi. And the reciprocal of undefined, let's do this undefined thing as 0 over 1, or 1 over 0. So the reciprocal of that would be 0. So where that asymptote is would be the new place for the cotangents. And we know the reciprocal of undefined, and it would look like that. And it's interesting that well, it should have hit right there. The reciprocal of 1 is 1, so that doesn't change anything there. The reciprocal of undefined is 0, so this becomes the center of my cotangent. All right. So let's talk about the rest of them. Let's go back. I want to talk more about this. If I have my tangent graph, here's negative pi over 2, and here's pi over 2. Asymptote, asymptote, up from left to right. That's my tangent graph, the normal one. For my cotangent graph, instead of the center of it being there, there's the first asymptote, and there's pi, and here's pi over 2. And it goes down from left to right. So this is your first period of cotangent, and this is your first period of tangent. Okay? I just wanted to make sure that I got one more example on that. We'll probably do some of that in class. When we get to finding the secant graph, we know that the secant graph and cosecant graph, there's your cosecant, cosecant and secant. Hopefully you recognize that the cosecant graph is the reciprocal of sine. So this is my sine graph, this top one. Wherever it hits 0, the reciprocal of 0 is undefined. So those become asymptotes. And we use those dotted lines as asymptotes. And we know that the reciprocal of 1, we know that 1 here on this axis, reciprocal of 1 is 1, reciprocal of a half is 2, and we get something that kind of looks like this. Reciprocal of negative 1 is negative 1. And they kind of look like parabolas, but they're really not, because they're a reflection or inverse of a trig, so they're not really parabolas. They kind of look like it, though. Now, the same thing goes for the secant graph. Anytime the cosine, which this is a cosine graph, goes through 0, it becomes an asymptote on its reciprocal. And the only difference between these two is that the positioning in the graph, basically. Notice that here the 0 is an asymptote, and for the secant it's one of the vertices of your secant graph. So wherever the zeros are in the original is the asymptotes for the reciprocal. All right, hey, look at me. There that is. Let's see if I pull that down a little bit so you can see those. And you can pause and look at those as much as you want. Again, they kind of look like parabolas, but they're not. Now, if I wanted to graph some of these that are not standard, let's take a look at this. I'm going to put it in Mr. Auto standard form and then write a bunch of things. Tangent of pi over 2 times x, getting the x by itself. We know our period here is pi because it's a tangent divided by pi over 2, which gives me a period of 2. And we have an amplitude of 1/2, which means it's going to be flatter. So I'm going to take my 0, which I'm going to put right here, and since my period is 2, I'm going to go with 1, 2, 3, 4 that way, positive 1 that way, 1, 2, 3, 4, negative 1 that way, which makes this a half, which makes this half. And so now I have my 5 points, and I know that my amplitude is a half, so I'm going to go with 2 lines being a half there, 2 lines being a negative half. So since we're going to be there, that's what it would look like. Okay. Because I call them halfsies because we find our 2 asymptotes. Halfsies is the middle, and then halfsies are where the amplitude goes. All right, let's take a look at this one. Again, I'm going to call this 0. We see that we have a secant moved pi to the left, so I have a negative pi is where I'm starting this at. And I'm going to call this 1, 2, 3, 4. I'm going to call this negative pi. And I know 1, 2, 3, 4, positive pi, because my period is still going to be 2 pi. It's just that on this one, it starts to the left. And we know that we're going to be 1 and negative 1 is our amplitude. So I'm going to draw in there my cosine. There's my cosine graph. And then wherever the asymptotes, or wherever the zeros are, is where the asymptotes go for. And so my secant graph, we only have half a period on that side. And it's going to look something like that. Now, if I extend out my cosine graph, which certainly could do, oops, it's there, I put negative 1. We can certainly extend, put another asymptote and another part in there. So these do continue on forever, so easily done. We'll do more of these in class. I was thinking maybe I would post another video of me doing one of each of these with some shifts in there with this. See you Thursday.